in class. So welcome to our CCNA1 meeting for today, April 26th. Are there any questions before we get started looking at a couple modules I want to talk to you about? Any questions about, I know, Jacob, I believe that you've had trouble with the skills exams. One thing I want to make sure you understand is a couple things. One, when you go to take the exam itself, it may ask you for what version of packet tracer you're using. Just make sure you choose 7.22 or higher. So like I said, when you go to take the exam, this basic communication exam, it may actually prompt you for what version. Let me turn off. I was editing some stuff, folks.
It let me in because when I click in the exam, it let me into that mode, but it doesn't show me. But I'm using the latest version of packet tracer, and I have it in different. Have it in the high and the core 7 the computer, and I have it in the core 5 computer. So, and I test it in both of them. It's doing the same thing.
Okay.
I think it might be the what do you call it, that it doesn't let me in because of the they call it the cookie. It might be that one's might be the case.
That could be.
I'm going to research into that to see.
I would do that. The other thing, have you ever had a previous version of packet tracer installed? So have you had a version previously?
I do not.
You do not. Okay. All right. Because one thing I will tell you, if you have an old version and then you install the new version, that can cause a lot of trouble. So this is just a good overall tip for everyone. Anytime you're upgrading packet tracer, uninstall the old version, reboot your machine, then install the new version. That way you won't have any problems with any types of problems there. But you shouldn't be having any problems with really the module exams if you've got packet tracer installed and loaded.
Well, I think maybe because I tried to install the version 7 and the computer tell me that I've already have the newest one. Did I want to replace it with the old one?
Okay,
so,
what I would do then, Jacob, is I would go into your add remove programs, remove all versions of packet tracer, anything that says Cisco packet tracer, and then reboot your machine and install just packet tracer 8 64-bit version. And remember, if you need to get packet tracer, you can always go to resources and then just go to packet tracer resources. And then you can download packet tracer download page right here will take you directly to the download. And then you can just download the 64-bit version 8, which you will need for some of the larger packet tracers that are in the new 7.02 curriculum. So I would suggest doing that, and that should probably fix your problems you're having.
That's exactly what they gave me. I installed 64-bit.
Okay.
So, and because I have Windows 10 and I have a core 7, the processor with 3.7. So the only thing I might try is that I might try the newest version, uninstall the newest one, and I try to install the old one and see if I can get it in that way. So right. I know because if I have the old one, if I have the latest one, 8.00, the 212 or something like that, if I want to install the old one, the computer tell me that I have the latest one. Did I want to keep it or I want to replace it?
Well, but here's the thing. Here's where you're going to run into trouble, and this is true for everybody. We're using version 7.02 of the curriculum. You must have version 8 of packet tracer to use the packet tracers in this course. So you're going to have to uninstall all the old versions, and you're going to have to go with just version 8 64-bit because that is required for the version of course that we're using. So that's not an option to use the old version. You've got to use packet tracer 8 64-bit version. So I would uninstall all the old versions, whatever version you have, reload your machine, restart your machine, and then install just 64-bit 8 clean. And that should fix your issues. Any other questions? Any other issues going on? I do want to real quickly, there's been, I think, some confusion about Just don't forget, folks, that your syllabus is available both on Canvas and NetAcad. And this does have your weekly assignments. Do know we've got a built-in week here, folks, for catch up, because I know some of you are behind. Many of you have not done anything in NetLabs yet. That's not optional. That's not going to be optional. You've got to go into NetLabs, and you've got to be doing labs inside NetLabs. So any lab that is bold, it must be completed on my NetLab system. That's the only way, folks, I know that you've done hands-on labs. And so I've got to have you as instructors doing that in my classes. Otherwise, I can't accredit you and say, yes, I want this instructor to be teaching the academy program. That's one way I can look. Now, the beauty of NetLabs is that I can actually drill down to the point where, and I'll log in real quick and show you, I can actually drill down and see individual commands that you have placed on the labs. So when I go into usage here, and let me try to pull a lab, I'll actually pull it from one of my other classes that I know that none of you will know them. So let's see, fall. Let's do this one. I'll show you. I've got it over here on another screen, so I'll show you in just a second. But let's see. Okay, so this is one of my students that was in a class this summer, and I'm able to actually go into the devices, and I can actually look at the session log for R1, and this system allows me to see every single command as I go down here. These are all the commands that were typed in by this user. So I can actually look and see whether or not you're doing the labs, whether or not you're actually doing what's correct. A lot of times, like, I'll use this to troubleshoot issues. So when someone uses, puts in the wrong router ID, or puts in, this is way beyond what we're doing right now. This is from the 3rd class, by the way. So by the end of the fall, you'll be able to do this, no problem. But this system allows me to see that. If you don't do your labs on this, I cannot see what you have actually done. So I want you to be aware that you need to make sure that all the labs on our syllabus that are in bold are to be completed on our NetLab system. Okay, and there've been only very few of you have actually gone into our NetLab system and used it. So please make sure you're using that system.
Even 3.7.10.
3.710 is, yes, it's on there. Let me make sure. I may have made a mistake.
It's a Wireshark one, I thought.
It's on there. It's on there though. 3.710 has been rewritten, so that's where you have to be careful. When I talked about doing the labs using, 3.710 is here, but you have to use the document that is in inside the lab itself. Now notice, don't think that when you log in here there's only 4 pods. There's 16 pods, everybody. So and by the way, right now ordering equipment, I've got 4 more pods ordered, but we're getting all kinds of delays in shipping of new equipment. So, but there's plenty of pods available. You'll just have to make sure when you actually do this lab that you use the document that's from inside of here, which is what I've stressed, because it's rewritten to only work, inside of here. So yes, that one is inside of here. Now, if you want to do it on your local machine too, that's fine. But I need to see it in here so that I can see that you're doing labs. Otherwise, I don't have any way of tracking your labs. I know you're turning things in, but that doesn't prove to me that you're really touching the devices or doing anything. You could be using just Packet Tracer, which Packet Tracer is a great program, but it's not the be all end all. It's not real equipment. Okay.
My experience with that is some of the that you have in the NetLab. My experience is that if I take the higher one, I see that it's slower, and then because I even time it when I was trying to get some operation to work on it for about 15 minutes, and it doesn't do anything. Then I come back sometimes when nobody is on the first one or the second one. It's more faster for me to do.
Now, all the pods should be the exact same speed. There's no difference in speed. I mean, now I will tell you, it takes a little while for these to boot because these are real devices. I mean, depending upon what's being booted, it can take a little while for it to boot. But there should be no speed difference in the pods. And I use, most of the time I use pod 16. A lot of times for when I'm doing demonstrations and doing things. And, you know, I don't really see any speed difference in pod 16 versus pod 1. So again, you'll see most people on pod 1 because they're using pod 1. This one in particular, you just got to give it time to boot, make sure all the devices boot, including that router, because it can take a little while for that router to boot up. And so just be aware. I usually try to give about 5 minutes at the beginning of the reservation to let everything boot up. But see, that's real gear too. You know, in the real world, you're not going to sit down at a router, turn it on, and it's going to be ready to use immediately. The other thing your students need to realize is in the real world, if you reboot a router, you're going to be turning off access to people for a good amount of time, a good chunk of time. So in the real world, that's something you only do as a last resort. If they get used to using nothing but packet tracer, they're like, oh, I can just reload the router. It's fine. It takes 30 seconds for it to come back up. And then they do that in the real world and their network's down for, 5-10 minutes and people are screaming at them. So they need to work with real gear to see how it really works in the real world. That's the scary thing of trying to rely on packet tracer only. So there's your course syllabus. It's right here, just like I said. I know we're into up into 8 through 10. I'm actually going to have your lectures. I've got module 7 is over here right now, about done. But we're going to talk a little bit about module 8 today and module 7. In fact, I'll probably just go straight into module 8 if we don't have any questions on the Ethernet. But I do want to cover one quick thing on Ethernet. So any other questions before we go on with lecture?
I have one question about the design of PCI. I think it's in module 6 or module 7. The PCI design of using it. In the olden days, they had a PCI that it can be on the 8-bit slots, and then they changed it to 16 and 32,
right,
and now 64. And now they have like I said, in the olden days, they don't have the memory to the PCI, but lately now they start to be designed some memory with the PCI. So, and I was thinking about it in design, actual design. If your motherboard is not compatible, which is another problem, or the power that the latest one is drawing, even if you have the slot in the motherboard that you can take it, might be another problems that from the practical experience that somebody may have to explore, even you are trying to design the fastest or the most powerful network.
Okay, and one of the things that you will see with network interface cards, especially when you start getting into servers, there's all kinds of, I'll give you a great example. We just bought a couple Dell servers, and on the Dell servers, they had integrated 10 gigabit NICs, but we also had a riser card that went to a series of 4 10 gigabit NICs. Of course, that was connected directly to the motherboard's backbone and all of that. But the riser board itself had an error, and we had a problem with the 10 gigabit NICs. They just would not show up. So we had to replace that motherboard. But that is something you need to be careful with as you start looking at servers and you start looking at network designs, that you look at the fact that your basically the backbone data paths support the speeds that are needed inside of there. So, and that again goes into your different types of PCI types and PCI, different types of PCI slots that you have. Okay. All right, let's talk a little bit about anybody else. Anybody got any questions? Let's talk a little bit about Ethernet. True, false. Ethernet is an 802.3 standard, or is the 802.3 standard. Everybody should say true. That is true. It is 802.3 standard. We also have, we know the 802.2 standards, which are responsible for the logical link control sublayer. So when we look at LLC and MAC, those are the 2 sublayers of the data link. I've talked extensively about the fact that now let's think about this. Have any of you ever touched an IP address? Have you ever held an IP address? It's
No.
no, that's a bit of a, you know, a joke question, but no, you can't. That's because it is a software component. It is a logical address. It's not a physical address. It's not something you can touch. The data link layer actually has components you can touch. A network interface card is a data link layer component. A switch is a data link layer component. When we look at the data link layer, we have the MAC sublayer that deals with access control and framing, but we've got to have a way for that media access control sublayer to talk to the network layer. And not only that, we have to do it across the spectrum of different speeds. So we've gone from 10 megabit Ethernet in my lifetime. I've literally worked with every single one of these, from 10 megabit up to 100 gigabit. I've even worked on 4 and 16 megabit token ring. I'm not that old. I'm not that young either, but I'm not that old. So it's been amazing how fast these technologies have evolved. But as we moved each one of these speeds up, as we changed the way 802.3 Ethernet worked so that it could support these faster speeds, we did not have to rewrite the entire network stack or the entire data link stack in the OSI model, because we had this 802.2 sublayer that acts as an intermediary between your hardware components and your software components. And that's the entire purpose. And by the way, now we've seen this 3 times. We've seen it in module 6, we've seen it here, we've seen it before. So I think I would know that 802.2 is the LLC sublayer and MAC is 802.3. 802.11 is our wireless Ethernet standards, and then 802.15 is what's called a WPAN, or wireless personal area networks. Great example of that I'll give you of a wireless personal area network is back when I was riding, even back when I got hit. This is a little morbid, but it's true. I had a device on my bicycle that sat on, it was a GPS that connected to my phone, and it constantly tracked where I was at. So one of the ways my wife knew something was wrong the day I got hit is the fact that my little dot was in the same spot for like 45 minutes. So, and now the bad news is earlier, a couple of weeks earlier, I had done that and just was a software error, but that is one of the ways that she knew. That's a wireless personal area network. Or if you've got heart rate monitor, I had a heart rate monitor that would also do my heart rate. That's a wireless personal area network. So it's a network that's within your personal area, which are pretty cool, quite honestly. So our MAC sublayer, we're going to look at framing, addressing, and error detection. So let's look, we talked a little bit about accessing methods or access methods. Do you remember, pull back up, and yes, I do love my whiteboard, folks. I know my handwriting's horrible, but CSMA CD. So carrier sense multiple access with collision detection. This is what our legacy or typical Ethernet used. Okay, so this is what we consider to be Ethernet. Can anybody explain to me what CSMA CD, how it works? The base method of how it works. Anthony, you want to explain it for us? Or give it a start? What is CSMA CD? Carrier sense multiple access with collision detection. All right, let me move over. This is from a lecture I did earlier today. Here's a great example. So I just posted our module 6 lecture, by the way, but carrier sense multiple access with collision detection is a contention-based access method. So what would happen is, like in this instance, A would look to see if the line was open and not in use. So that's the carrier sense portion. If it's not, it would then send. Now, the bad news is D could look and see it empty at the same time A looks and sees it empty, and they could both send, and you could end up with a collision. If that happens, the first machine to see it, which by the way, the collision results in what's called a runt frame, or a frame that's smaller than 64K, it would send out what's called a jam packet to tell everybody, whoa, 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 there's been a collision. Everybody back off. That's even called the back off algorithm. Perform the back off algorithm. wait around an amount of time before you try to do carrier sense again. Now, this method was contention based because you did have the possibility for collisions. We also had another method that is used with wireless LANs, which is CSMA-CA, collision avoidance. So carrier sense, multiple access, collision avoidance, which is basically set up for wireless Ethernet or wireless. And this says, hey, before you try to send, signal your intent to send. So in other words, I'll go, hey, I'm going to send something. Then the access point says, okay, everybody, Kelly's going to send. And then I send. Now, the problem with that is because you're doing collision avoidance, that wait time is adding overhead. So it's actually slower than CSMA-CD, but you technically shouldn't have collisions, although you could. And then last but not least, there was an old method that was called token passing. And I always go back to, Lord of the Flies, where we're passing the conch shell around. If you have the conch, you can talk. If you don't, then you cannot. This was actually a controlled access method because you should never have collisions because you had the token. If you didn't have the token, you couldn't talk. You had the token, you could talk. There were even ways on token passing networks to have multiple tokens going at one time so that you could speed things up. The only reason that we ended up with Ethernet, all right, I got something in chat here. Let me see what we got here. Yep, token ring with Nobel networks. Yep, and I actually worked with token ring with Nobel networks. And if you did work with token ring, you'll remember that you could not plug in a NIC while the machine was on, or you could actually blow the NIC out, or it'd actually destroy the NIC. There were all kind of little things that you could get in trouble with token ring. But yes, I actually supported a token ring network in a classroom. And by default, honestly, token ring should be faster. It should be a better system than Ethernet because it's not contention based. But the problem was, since it was proprietary to proprietary to IBM, and they didn't allow third-party vendors to create the network interface cards and did not allow generic vendors, you ended up with so much expense that Ethernet just got faster and faster. And so even with the collisions, it was better, it was faster. So here's our different types of Ethernet: 802.3U, which is fast Ethernet; 802.3Z, which is gigabit Ethernet; 802.3AB, which is gigabit over copper, and then versus gigabit over fiber; 802.3AE, which is 10 gig, and then it goes on now to where we're all the way up to 40 gig and 100 gig. And I think, if I'm not mistaken, I recently saw a move towards 200 gig send and receive Ethernet. So as long as we can replace these MAC sublayers and we can continue to work with this logical link control sublayer, we're golden with Ethernet. So here's our Ethernet frame. This is a typical frame. 64 bytes is the minimum size. Anything below that is called a runt, or it's considered a collision fragment. So if you do have a collision for some reason, it creates a frame that's less than 64K. And then anything above 18 bytes is considered a jumbo frame. And you also have, in real world, we actually can use jumbo frames, especially in our data centers. We can increase the size of our frames on the data center backbone where we've got 100 gig connections and 200 gig connections to our devices. Inside of this frame, remember the data right here, this 46 to 1500 bytes, is all that information from the application, presentation, session, transport, and network layers. So all of that is bundled up in those little Russian dolls and placed in there as data. And then we have our destination MAC address, which is 48 bits, okay, 8 times 6, our source MAC address, and then the frame check sequence. And one of the reasons the destination MAC address is first is because of historically every device, when a frame went by, so looking at our network that I showed you over here, historically in our actual Ethernet networks that were based on a bus like this, every time a frame went by, every device had to look at it. So if A was sending to C, and it went by B, B would have to bring that frame in and look at it at least up to the destination MAC address and say, is this for me? If the answer is no, it discards it. If the answer is yes, for instance, C would see that it is, it would then dig down deeper and say, okay, well, I know that the source and destination MAC addresses were correct. Then inside of here, there would be, of course, our destination IP header, because our layer 3 headers would be in here, and our source IP headers. And so C would look at it and say, is this destined for my IP address? If the answer is yes, I take off that header and then look inside of that and see where to pass it up to at the transport and application layers. So that's why when Ethernet was created, the destination MAC address was placed first in the frame field. Otherwise, devices would be looking at frames that they would eventually discard further and more in depth than they would need to do otherwise. Type length, this tells you what's above it. So O by 800, 0 by 800 for IPv4, 0 by 86 DD for IPv6, and then ARP, which we will learn more about later, is 0 by 806 with address resolution protocol. And then last but not least is this frame check sequence, or CRC, cyclical redundancy check, which runs an algorithm against the frame and gets a number. And then on the receiving end, you run the algorithm against the frame again. If they match, then it ensures the frame was not damaged in transit. So it's basically an integrity check to make sure that the frame was not changed. All right. So MAC addresses are hexadecimal. So instead of seeing it in decimal or binary, they're in hex 0 through F. You can see how we normally write them. There's other ways to write them too. For instance, let me see where this is going to pop up at my command prompt. I don't know where it went to. For some reason, my command prompt is not showing. There it goes. Got it. ipconfig/all. If you do a ipconfig/all, you can actually see your IP address and your MAC address. So for instance, right now on my machine, you can see that my machine has the MAC address DE9EF3 37B647. So you'll notice it says Intel. The MAC address is made up of 48 bits. There are 24 bits, which are the first 24 bits are the OUI, or the organizational unique identifier. So the first 12 hex there. And if we go, I'll show you something really neat. Wireshark has a special thing that is an OUI lookup. So I can actually come over here and I can say, okay, D8-9E, D8-9E dash, let's see what my last one was here, F3. Find, it's going to tell you should tell you it's an Intel NIC. Nope, it's Dell. So this tells you that this is a NIC that was registered to the Dell Corporation. And then the last 24 bits are the serial number Dell assigned to this NIC, or that have been assigned to this NIC. So this particular NIC was sold to Dell and it is on a Dell machine. The neat thing about this is, if you look here, here's a VirtualBox host adapter. So if I do 0A0027, so 0A-00-27 and search it, it should say no match. Well, it actually should have probably said VirtualBox. Let's see if I had a VM there, this actual 00F. Yes, let's do 00-50-53, wasn't it? 56. Okay, 56. See, it says VMware, and that's actually one of the ways that people find your honeypot or see a box that's running in VMware instead of being a real device. You can actually search the OUI, and if you do and find out that it's VMware Inc., then that tells you that that's actually a virtual adapter. So that's an adapter that's associated with my installation of VMware Workstation. So when we look at MAC addresses are based upon an OUI 24 bits and 24 bits that are vendor assigned. These are hard coded. So although you can spoof them with software, by default, they're hard coded in the NIC. So if you are, need to track someone on your local network, it's pretty easy to do so with an OUI and a MAC address, or just a MAC address. You can actually find out a particular machine. Questions about MAC addresses? We'll learn how you find MAC addresses using ARP, but right now, just suffice to say, you've got to have a MAC address in order to send anything, because you've got to have the MAC address for your destination and source frame information in Ethernet. So let's take a look here. If this was actually a hub, now this is more like you watch this switch, the way it works. This switch is acting like a hub, or like a switch that's just been turned on, because when that frame comes in, it sent it out every port except for the one it came in on. Once this switch actually propagates its MAC address table, or is able to fill in the MAC address table with all the MAC addresses, it would not do this. It would only have sent this from H1 to H3, because it would know that information. Just like all addresses, there are unicast MAC addresses. So I got a chat here, folks. If you ask a chat, yep, there's another one. Standards.OUI text. That's another one. It's a good one that can be used. It tells you all the ones. You can actually look them up, so you can actually see all the different ones. So it's pretty easy to find who is the owner of a particular NIC. That actually, by the way, we'll learn as we move forward, caused real issues with IPv6, because in the beginning with IPv6, the host portion of the address was being created using the originator's MAC address, and that was allowing people to be tracked if they were using IPv6, which could be a real problem if you live in a country where people were tracking what you were saying and were trying to find you quickly. So unicast MAC addresses, that is a single MAC address assigned to a single device. So in this case, this server 1200 is the MAC address shown here on the right, and the host is the MAC address shown on the left. And if the switch has a correctly populated MAC address table, it would send it only from H1 to the server, right? Broadcast, which is all Fs, I say, so kind of like a cat screeching at you. But if the MAC address is all Fs, or 48 ones in binary, what the switch will do is it will send it out all ports except for the port it came in on. And the reason it doesn't send it out on the port it came in on is because the switch assumes that this is a bus network, that every host that needed to see it would see it already before it came into the switch. So it's making an assumption that that is a bus network. Then multicast is sum one to sum. And to join a multicast group typically requires you to be running an application, and then your NIC or the application will start listening to the MAC address that is associated with the multicast group. We even, as I mentioned in lecture that I have for this chapter, we even have the ability to block off certain ports. So even though this particular diagram shows it going out to these two hosts, if we do multicast pruning, we actually can make it to where these two ports would not receive this multicast, because all they're doing is receiving it and dropping it, because they don't have an application running that. So on a switch, here's our MAC address table by default, has nothing in it. As the MAC addresses, as devices communicate with one another, so when A sends something to D, the switch would put that MAC address of the source into port 1 and would flood it out all ports except for the one it came in on, because it doesn't know where D is at. When D responds to that information, it would then add D's MAC address into the table right here. And now it knows if it needs to send something from A to D or D to A, it would just do it directly to them. And eventually our goal, what we want, is for the switch to know the MAC addresses of all devices on the ports associated with it. There are two videos here, but I will tell you that this, again, is one of my favorite activities. I talked about it in the lecture, but Basically, you use this to determine how switches will deal with traffic. So in this instance, we've got the source MAC address is 0E and the destination is 0F. So we know here that if 0E sends something out, it's going to come up. This is a hub, by the way, which means it's going to go up to port FA9 and also over to 0F. So where will this particular device forward the frame? Well, the answer in this case should be nowhere, because it's going from 0E to 0F. And so what it's going to do, it's going to add the source MAC address. Okay. And it's a unicast, but it's going to be dropped at the switch. The reason being, the switch knows that 0F is already on this port. So that should be the correct answer, because even though it come up here, the switch looked at the MAC address table and said, oh, 0F is on port FA9, and dropped that frame. That is about the only case where you're going to have a frame that's a unicast get dropped when it comes in. Then you do a new problem. 0B going to 0D. All right, so let's look at our table here. So 0B is known. Okay, that's on port 3. 0D is known as on port 7. So we know this is a unicast frame, and it's going to a known port, known address on a port. So it's going to go to FA07 or FA7. It's going to be sent to a specific port only. You're not going to add the MAC address to the table because it's already in the table for the source. It's not a broadcast because it's not all Fs. It's not a unicast that's flooded, and it's not going to be dropped. Check. New problem. Let's look here. 0C going to 0A. Once again, it's a unicast. Both of them are known. So it's going to go here. It's going to go right there. So it's unicast sent to specific port. New problem. And it's so on and so forth until your students can get tired of it. This is a very, very important activity. You could see these types of questions on the CCNA exam to try to understand how the switch uses its MAC address table. So I would spend time with this, and I would have your students spend time with this, because it is an excellent little activity. Any questions about this? So let me pop up something here. Pop up a notepad. I'm not sure why I keep having issues with my notepad won't pop up. Okay, so when the switch first boots up, okay, brand new switch, it has nothing in the MAC table, nothing in the MAC address. By the way, it's also sometimes called the content addressable memory table, or CAM table. When there's nothing in that table, it has to flood out all ports except when it came in on. Frame came in on. All right. It will then add the source MAC to incoming ports. And once it learns all MACs, forwards only to the correct port. Unless it is what? What will always be forwarded to all ports except for the one it came in on? Anybody?
Unicast.
Broadcast. Broadcasts are always forwarded to all ports except the one that came in on. This is why originated. Okay. This is why, by the way, have you ever heard of the broadcast storm? This is why broadcast storms are so evil. First off, let's go back. I do want to show you something. Let's go all the way back to right up here, and let's look at a frame. Okay. Let's actually go back up here. Let's look at a frame. In this frame field, do you see anywhere that there's a time to live? Is there any kind of TTL field? Have I mentioned at layer 2 anything at all about decrementing a time to live field every time a frame goes through a switch? The answer to that is no, I have not. And that is because this frame has no time to live feature. It has no TTL. It has nothing that's decremented, which means once a broadcast starts going through a network, and you'll find out later when we connect multiple switches together. So if you end up in a situation to where you've got a network not running spanning tree, of course, I know all about spanning tree, folks, so I know spanning tree is an item. But imagine a network to where we've got spanning tree turned off for some reason. We've got these connections here. We've got a PC here, that PC there, got PC over here. Let's imagine that PCA here sends out a broadcast. So broadcast, let's do red because it's evil. So we're going to go in here and we're going to send out a broadcast. That broadcast comes in. It's going to go out all ports except for the one that came out in. So it's going to go out here. It's going to go out here. Okay, so I'm just going to do red. So it's going this way. Well, the problem is it came in here. So it gets sent out here and sent out here in red. Well, then now let's switch over to blue, because now what happens is it came in here, but it's got to come back out here. So it's going to go out here again. And now it's in here. So now it's going to go back out here, change colors. And suddenly you've got right here a broadcast storm going on, which can overwhelm your links. We're going to learn how to mitigate those. But that is a big problem at layer 2. It's the concept of a broadcast storm, because there's no time to live field. Once a frame gets out here and starts bouncing around, it bounces forever until you break the loop. So we'll talk all about ways to fix that later, but that is a major issue at layer 2 that we need to be aware of. Okay. Cisco, by the way, has methods for dealing with ingress and egress frames. In other words, when a frame comes in, it's got to forward it to another destination. The most common method, and the one they like to use the most, is called store and forward, and that's where it brings the entire frame into the switch, runs the CRC, ensures the frame has not been damaged in transit, and then sends it out to the destination. Now, that is slower because it has to look at the entire frame before it sends it. But with the correct ASICs and processing power, the switches can do this in pretty much real time. So they're able to keep up with the necessary computations that are needed. However, on some of our older switches that were not able to do it, they did use a method called cut through. And with cut through, there were basically 2 different ways. One is forwarded as soon as you got at least the destination address come in. Once that came in, you'd forward it. Or another method was called fragment free, which said as soon as you receive 64 bytes of the frame, send it on, start sending it, because really, you remember, we talked about anything that's more than 64 bytes can't be a runt. So it's not more than likely going to be a collision. Well, it's not going to be a collision. So we assume that the frame is okay if it's at least 64 bytes in size. Now, with these 2 methods, fast forward and fragment free, it is possible that you could forward a frame that was in fact damaged and would have to be retransmitted. But what would happen is the destination would get it, would run the CRC against the frame that it received. If the CRC didn't match the sent frame, it would then drop it, and upper layer protocols would have to be invoked in order to do a retransmission. And then memory buffers here, we talked about this is how modern networks can be as quick as they are. In our networks, A can send to D while B is sending to C, because the ports themselves have memory that allows, if D and A are talking and B sends something to A, the switch can hold it until the port is available to send it to A. So we can have port-based memory that's each individual port has its own chunk of memory, or we have shared memory where each individual port uses a shared pool of memory. When we connect devices onto a switch, they're going to negotiate 2 different items. One is duplex and one is speed. I'm not a big fan of letting devices do their own negotiation, especially what I typically do is hard set it on the switch side and then leave it to negotiate on the device side. Most of the time, auto negotiation works fine. The issues we had were in the old with old fax machines or older printers or weird IoT devices. Sometimes don't like to play well with auto negotiation. So if you set it on your switch, say duplex full, speed 1000, then when the device tries to negotiate, the switch simply says, no, we're going to be a full duplex and we're going to run at 1000 megabits per second. The device can take it or leave it. And that usually is what we do in our modern networks. Now, last but not least, in this particular chapter, we talk about MDIX or crossover. By default, if you connect two like devices, a switch to a switch, you should be using a crossover cable. However, with modern networks today, we have what is called auto MDIX or auto cross. So even if you put a straight through cable between two of our 2960 switches, they will come up because it sees that it's connected to a like device and will cross over the send and receive pairs so that you have a full duplex connection between the two devices. Now, if you got an older device, it may not support MDIX. So 2950 switches, some older switches may not support it. So be aware, if you ever connect a device with a straight through and you're like, well, it should be auto crossing and it's not, it's two like devices, you may actually need a crossover cable. Any questions on Ethernet? Any questions at all? Okay. Any questions on anything modules 1 through 7 so far? None? Okay. What I'm going to do then is I'm going to get out for you lectures for 8, 9, and 10. I'll let you review those, be working on the labs, and then we can discuss anything that you have on those next week and continue as we're moving forward. Again, I know many of you are behind. That's fine. The due dates are not absolute set in stone. They are designed to give you the ability to at least have a marker to go by. I want you to know that most people end up behind a little bit in these classes. That's fine. I understand that. Let's do try to work and stay caught up as best we can. That way, because we're on a pretty tight schedule with your classes for the summer. You've got CCNA 2 right after this class. The good news is, as we move into CCNA 2, it gets easier because you understand how to get around in NetAcad. You understand how to get around in NetLabs. So life gets a little easier for us as we move forward into 2 and 3. But I just don't want you to get so far behind that you have to really, really push to catch up. Because I know, like, if you're like me, you've got graduation coming up in a couple weeks. You've got summer schedule, summer session coming up. I don't know how many of you work in the summer, but that's probably one of our busiest months. Actually, for us, it's summer. Okay, any questions? Anyone?
Well, Professor Cotto,
Yes, sir.
I only have 10 more days for grading, and then I'll be a student.
Yeah, good. Yeah, it's people always ask me, you're off in the summer, right? And I'm like, no, actually, I'm teaching 5 classes this summer. Yeah, my summer schedule is usually my hardest time simply because, and in fact, it's summer is actually, I hate to say this, it's easier under COVID because I'm not traveling. Typically, I would be at Skills USA for a week. I would be at Cisco Live for a week. I would be at our Cisco Academy partner meeting for a week. So, typically in the summer, I'm flying all over the United States, going to conferences, and trying to teach, but not this semester. So I think we'll finally get back to maybe normal next year. So I'm actually putting it as my professional development, going to Cisco Live. By the way, if you've never been to Cisco Live, that is a wonderful conference to go to if you want to really learn in depth on Cisco's technologies and what they're doing. So, okay, I'm gonna stop the recording, everybody.